All right, welcome to lesson 14.3, wave behavior. We're going to be talking about what happens when a wave encounters a more dense medium, what happens when a wave encounters a less dense medium, what happens when two waves encounter one another, like two waves come at each other. What happens if two waves are approaching each other with very specific frequencies? We get standing waves. And then you also will get standing waves on a surface. So we're going to be talking about wave behavior, how waves behave when they interact with something more dense, less dense, with themselves. So first of all, we're going to talk about when waves meet each other. This first wave right here I've got coming in, we call this the incident wave. The incident wave is the initial wave that starts this whole process. After it encounters the boundary right here, we get this wave, this smaller wave that goes out. This is called the transmitted or refracted wave. Now so the incident wave rolls in, hits the boundary, some of the wave goes through and some of it bounces back. This bounce back we call the reflected wave. Now all of these have a specific, all these different waves have a specific name. So there's three of them: incident wave, transmitted wave, reflected wave, all depending upon where they came from, where they're going to. Now what I want you to notice when it goes from a less dense medium to a more dense medium is that look at the reflection. My incident comes in, the reflection comes back on the opposite side. Look over here when you're going from a more dense to a less dense. The reflection comes back on the same side. Now we're just looking at transverse waves, but the same thing is true for longitudinal waves as well. The reflection will come back the same. So if it comes on the top, it's going to come back on the top. It comes in on the top, it comes back on the bottom. That's the difference between, that's one of the differences between if you're going from a more dense to less dense to more dense. Another thing that is similar, the reflection is always smaller. It can't be the same size because it's giving some of its energy to the transmission. So a big wave comes in, it transmits some of the energy through the boundary, and some of it gets reflected back. Same with here. It comes in very medium size, but always goes back smaller. The reflection is always going to be smaller than incident. Now the transmitted wave, now that's something else that's different. So not only does it come back on different sides depending upon whether you go from less dense to more dense, but look at the transmission. The transmission here, this wave comes in very large and then it gets very small. This wave, the transmitted wave, is smaller. If we go into a less dense medium, you'll notice that the transmitted wave is bigger. So it's smaller on the opposite side. This one's smaller and on the same side. So that's a common question. Compare and contrast waves that meet less dense medium or more dense medium. They're the same in the fact that their reflections are smaller. They are different in the fact that their reflections are upright. In this case, we call this upright. It goes back on the same side. as opposed to here, the reflection is inverted. Now, so here we have a couple of things. Incident wave. Wave that starts it off. The reflected wave. Bounces off the boundary. The transmitted wave, that's the one that goes through boundary. Now, next we have the principle of superposition. Superposition is when two waves come together, they add up. They can also subtract too. So right here, principle of superposition, two waves that meet, add or subtract. So these two waves are physically adding because they're both on top here. So I've got this smaller wave coming in here, and if we were to actually measure its height, and then I've got a larger wave coming in, these numbers physically add. So if this, let's say this wave was like 6 centimeters tall, and this wave here was 8 centimeters, these two waves added together, when they come together, should equal 14 centimeters. That's what the principle of superposition is, that they physically add together. Now I've got a couple of interesting videos that I found online that kind of show this in a little bit more. So if they come together and they make a bigger wave, we call that constructive interference. If they come together and they make a bigger wave, like these just did, I've got the first wave at the top, second wave in the middle, and then their addition. If they come together and make a larger wave, that's called constructive interference. Now I'm just going to pause it. And it's interesting to note that where my marker is, you can take any point on this wave and add it to any point on this wave, and it should equal the third wave. So let's take this right here. See how this is 1 unit high? So you look down here, this one's like 0.2. So when you add them together, it should be 1.2. Good. Look over here. This one is 2 units tall. This one is 1 2/3. So 2 plus 1 2/3 is going to be 3 2/3. So you go 1, 2, 3 2/3. So every single spot along this, at every single point in time, they will add up. Now if you've got two waves that are on opposite sides, so you've got one that's a wave on top and you've got one that's a wave on the bottom, we call that destructive interference. So constructive is when they come together to make a bigger one. Destructive is when they come together and they make a smaller wave, and they can actually physically cancel out. So focus on my mouse pointer down here as these things come together. You'll notice that right around here they almost cancel each other out. And at any point in time you can physically subtract these. So right here I've got, this is positive 2, and then I've got negative 2, so positive 2 right here plus negative 2 right here, and you get 0. So the principle of superposition. Constructive and destructive interference. Waves add up. Interference. That's when waves interfere. It's when they modify the other wave. Constructive, when they make a bigger wave. Destructive interference. Two waves make a smaller wave. Now, we can have two waves coming at each other that are very special. Like I've got, if you look in this picture right here, there's a blue wave that's traveling to the right. And you'll look and you'll see a red wave that's traveling to the left. If they have the same frequency, and they've got, which means if they're in the same medium, they'll have the same velocity too. Same wavelength. You get what's called a standing wave. It's alternating constructive and destructive interference. So these two waves coming together, you get a string flapping back and forth like this. This is called a standing wave. Now you'll notice this point right here. This point that doesn't move, we call this a node. And this point, which moves quite a lot, we call this an antinode. Nodes and antinodes. Nodes don't move. They stand for no movement. Antinodes, they move quite a bit. Now, standing waves can take all shapes and forms. So you can get a standing wave, as long as you, like a standing wave here, we've got a node on either end and an antinode. And this thing just flaps back and forth like a guitar string. Here we've got a node in the middle. So if anybody plays guitar and you're familiar with harmonics, this is where you've got nodes on the ends again, and you've got another node in the center, and then here you've got two antinodes. Here we've got three antinodes, 4, 5, 6, 7, right on down the line. We can get multiple different standing waves on a single string. Not only can you get them on a string, but you can get them in 2 dimensions as well. This is a surface like a membrane, and what's really interesting to note is you'll see right here, maybe I'll do it in green, that spot never moves. And not only that spot, but if you were to cross this right here, and then right here, these spots on this drum surface are not moving. And I've got a really interesting video to show you too. There was a bridge that was constructed in Tacoma, Washington, that when the wind would blow, it would set up a standing wave across its surface. Now, I'll fast forward a little bit. And then there's a node on this bridge. If you were to look right down the center line, that's what's called the nodal line. This whole thing is twisting back and forth around that line. So if you were walking on this, like this guy right here, he's a professor, a civil engineering professor that went to check it out. He's walking down that center nodal line, and he was able to do that. Eventually, the bridge, I think it did it for like a half an hour. And this concrete and steel was bending immensely. It's really flexible stuff. But it can't take it for long, and the bridge ended up collapsing. So we can have standing waves. So node, no movement. Antinode, maximum movement. Standing wave, wavefront. We'll leave wavefront off of this for right now.